This is section 2.2, and the title of the section is Limit of a Function and Limit Laws. So we're going to kind of go through and talk about what a limit is, and then start working with limits and getting some rules for how to do that. So if we look at this rational function, how does this function, x squared minus 1 over x minus 1, behave near x equals 1? And so we've learned in math prior to now that we can't exist if x is 1. If you plug in 1 there, you're going to get 0, and that's undefined. But what's happening as we get close to x is 1? So in looking at that, we know that it's defined, like I said, for all reals except x equals 1. Now, we can simplify it, and this is one of the techniques that we'll use algebraically. Let's factor the top, and we can factor it into x minus 1 and x plus 1. Difference of two squares, and then we can cancel those out, and we are left with y equals x plus 1. Y equals x plus 1 is our original graph with the point 1, 2 removed. And so if we think about it, it's this. We have a hole. If you graphed it on your calculator, you're not going to see that hole, but if you tried to find out what the graph looks like when x is 1, it'll tell you it's undefined. But you can figure out what is it getting close to. And so in this little chart here, the closer x gets to 1, so here we are coming in on either side, but we're trying to get close to 1. What are we getting close to over on the y side? We're getting close to 2. We don't actually reach there because it's undefined, but we're getting very close. That's what the limit is saying. The limit as x approaches 1, that's what that arrow tells you to read, of this function is 2. When you get close to 1, the y values get close to 2. L is the limit. So that's the idea of the limit. We have some limit laws here, and you should go over those. But what it's saying, it should make kind of sense. If it says here, if you have the limit as x approaches c of an f of x, and that equals L, and then you have the limit as x approaches c of g of x, and that's a different limit, then you can add those. So the limit of that function plus that function is the sum of the limits. Likewise, the difference of these, if you're taking the limit, is the difference of the limits. You can do it with the constant multiple rule. If you have the limit as you approach c of some number times a function, then it is that number times the limit. So you can go through these and see that that should algebraically make sense to you. Let's look at some strategies for evaluating limits right now. So if we cannot direct substitute, in other words, whatever we're approaching here, if it's a polynomial, you can directly substitute that number in, you get something, that's your limit. But when you have rational functions like this, you can't direct substitute because you will get 0 on the bottom sometimes. Sometimes it would work, but in this case, 1 squared minus 1, that gives us 0. All right, so then if we factor the top and factor the bottom, what do we get? So if we factor the top, we will get x plus 2 times x minus 1. On the bottom, if we pull out x, we have x times x minus 1. Those will cancel out. We're now left with x plus 2 over x. Now the limit as x approaches 1 of this function, we can plug 1 in, and we get 1 plus 2 is 3 over 1 is 1. So the limit is 3. And if you were to put it in the calculator and look at it, that's what you would get, that this is approaching. If you looked in your table, closer you got to 1, the closer you're going to get to 3 on the y value. How about when you have a radical? If we have something like this, one thing you want to look, so we can't plug in 0, obviously, so we can't direct substitute. The factoring is not going to help us. But if we create a common factor by multiplying the top and bottom by the conjugate of the radical expression, So here's our radical expression. And a conjugate is you write the same function, but you change the sign. And what that's going to do is help us get rid of things. So we're going to multiply by the same thing, top and bottom. Square root of x squared plus 100 plus 10 over itself. That's like multiplying by 1, so that's legal. All right, on the top, when you multiply a radical by a radical, you get what's inside. You're not going to have a middle term. You won't, if you're using FOIL, those cancel out. So we just have that times that, and then 10 times 10, which is a minus 100. On the bottom, we're going to write the x squared out here and leave this just as it is. Now, the 100 and the minus 100 cancel out. So now we've got x squared over x squared, and we've got that thing there that I didn't write. All right, now can we plug in 0? Can we plug in 0? We can't here, but here the x squareds go away, because if we had plugged in 0 here, that whole bottom would still go to 0. So these are now gone, and we have 1 over that denominator. We can plug in 0 for x. We get square root of 100, which is 10. 10 plus 10 is 20, so our limit is 1 over 20. So algebraically, that's two techniques, just factoring and sometimes multiplying by the conjugate. The sandwich theorem is something that we need to look at. So if we look at this picture, this says, suppose that f of x falls between g of x and h of x. That's what that's saying. And except that's valid for all x's in some interval containing c, except possibly at x equals c itself. And they say, suppose that the limit as x approaches c of g of x equals the h of x as we approach, and that's equal to L. If that's true, if this one and this one are equal to L, and this f of x is sandwiched in between these two, then that limit as you approach c is also going to be L. And if you look at it here, here is, that's a function in the red, here's the yellow, and here is a blue function squinched in there. And the limit for all of them is equal to 1 as x approaches 0. So even if you don't know anything about this blue one, because of the sandwich theorem, you could determine that. It's also called the squeeze theorem. So that's something to remember. All right, let's go look at our problems and see what we're doing. All right, here we have number 1 for the graph g of x below. So this whole blue thing is g of x. And they want us to find the limit as x approaches 5, x approaches 1, x approaches 4. So you're literally looking at your graph. So as x gets close to 5, where is the graph going? Well, the graph on either side is coming to y equals 0. So 0 is your answer there. B part, as x approaches 1. So as we go on the x-axis and we get to 1, coming from the left, if the function's coming from the left when x is 1, you're up here at 5. If you're coming in from the right, you're at 0. If these numbers are not the same, then the limit does not exist. It has to be the same on the right and the left. As we approach 4, where is the function going? Function going to 4 from the left and 4 from the right, so the limit is at 4. And please note, there's an open circle there. The function does not have to be defined there for the limit to exist there. All right, let's look at number 2. Which of the following statements are true and which are false? So here's our function. The limit as x approaches 0 exists. So as x goes to 0, the function on either the left or the right is ending up at the same point. So that's true. The limit as x approaches 0 of f of x equals 0. That would mean you would have to be ending up here. We are not. So that's false. The limit as x approaches 0 is -1. That is correct. From either side, the function is ending up at -1. D part. The limit as x approaches 1 is 1. So if we go over here and we go toward 1, from the left we're ending up here, from the right we're up here. Different numbers. So that is false. The limit as x approaches 1 is 0. That's false, because we said it doesn't exist. The limit as x approaches x sub 0 exists at every point x sub 0 in -1 to 1. So from -1 to 1, the limit exists everywhere. Remember, it doesn't have to be defined, but everywhere there, the limit exists. All right, let's move. Let's see. Oh, that was just the answers. All right, number 3. The limit as x approaches -1 of this polynomial. If it's a polynomial, you simply plug in the -1 for every x and evaluate. In this one, we get -10. Number 4. We've got a rational function. Can we plug in 1? Yes, 1 plus 5 is 6, so there's not an issue with something not being defined. So we plug it in both places, we get 3 over 6. That should be 1/2. So you'll choose A and put 1/2 in the answer box. Number 5, the limit as y approaches -9 of 18 minus y to the 4/3. We can put -9 in there and we can evaluate. And so that's what we do. And 18 plus 9 is 27. 27 to the 4/3 is like the cube root of 27, which is 3. And 3 to the 4th is 81. So your answer would be 81. Number 6. Now immediately we see radical and we think, oh, do we have to do that conjugate thing? But we always want to try the direct substitution and see if it works. The limit as h approaches 0 of 2 over this. Well, if I put 0 in there, then I end up with the square root of 1. That's doable. So I'll do that, and I've got 2 over the square root of 1 plus 1. That's 2 over 2, so my answer is 1. Number 7. Can we direct substitute? Can I put -2 in for x cubed and 2x squared? When I do, I get -8 plus 8. So I cannot do that. So then I look to factoring. On the top, if I take out -2, I get x plus 2. If I take out x squared here, because that's what's common, I'm left with x plus 2. That works out nicely. Cancel those out. You have -2 over x squared. So now you're taking the limit as x approaches -2 of -2 over x squared. We'll plug in. We end up with -2 over 4, which is -1/2. So we're good. All right, let's look at number 8. Number 8, as the limit as x approaches 225 of this. Well, if I put 225 for this x on the bottom, I end up with 0. So I know I cannot just plug in. So I'm gonna, now this one you might not have thought of this strategy, but now having seen it, you will. I'm gonna rewrite the denominator. I know this is on top, and this is x minus 225. If I do square root of x minus 15 times the square root of x plus 15, what does that give me? That's x, I don't have a middle term, and that's minus 225. So that's legal. I can just rewrite that, and I do that because then these can cancel out. Now I'm left with 1 over the square root of x plus 15. If I plug in 225 now, I've got the square root of 225, which is 15, plus 15, so I've got 1 over 30. Again, because you think maybe 15 is the square root of 225, so what can I do? And we rewrote the denominator. Number 9, can we plug in the limit as x approaches 2? On the denominator, we cannot put 2 in there because we would get 0. So now we're going to use that conjugate idea. So we're going to multiply both top and bottom by the conjugate of this numerator. That will be square root of x squared plus 21 plus 5 over itself. So when we multiply this out, we get x squared plus 21 minus 25. If I go ahead and combine those two, I get x squared minus 4 over this. Now I can factor this again and get x minus 2 times x plus 2. Those two are gone, and I have x plus 2 over this radical plus 5. Limit as x approaches 2. I can now plug in my 2 for x. I get 4 plus 21 there. That's square root of 25. That's 5 plus 5 is 10. 4/10 reduces to 2 over 5. So that takes a little bit of algebra, but it definitely gets you to the answer. All right, let's move up and see what 10 is. 10 and 11 have some trig functions in them. The limit as x approaches 0 of 6 sine x minus 1. Can we direct substitute? We should be able to. The limit, if we take the sine of 0, that's 0. So we have limit as x approaches 0. Here we plugged in the 0. That goes to 0, and we are left with the negative 1. Number 11, can we put 0 in the denominator? Cosine of 0 is 1, so that's going to be okay. So we plug in 0 here, 0 here, and 0 here. So this is 5 plus 0 plus sine of 0 is 1. Sine of 0 is 0. So sorry. And so that's gone and that's gone. So we just have 5. Down here, cosine of 0 is 1, so we have 6 times 1. So we have 5 over 6. So it's good to remember your sines and cosines and at least the quadrantal angles on those. That will be helpful. Number 12, as x approaches negative 4 pi. So we're just going to literally plug in and see what we get. So if I put negative 4 pi for x here and cosine of negative 4 pi plus 4 pi here, that becomes 0. And remember, cosine of 0 is 1. Over here, there's not much I can do about that. 1 times that is just that, and that is our answer. Okay. 13 and 14, we are using that form that we saw in 2.1. Limits of this form occur frequently in calculus. Estimate or evaluate this for the given value of x and the function of x. So the function, the f of x, this piece here is x squared. And this x happens to be 6. So we'll say limit as h approaches 0. We'll put in 6 plus h squared because that's our f of x minus 6 squared over h. So this is the form that we're doing. Hopefully that makes sense. Then we'll square this. We get 36 plus 12h plus h squared minus 36. Those two cancel out. It's very similar to what we encountered in 2.1. And then we have 12h plus h squared over h. We still can't plug in because that h is there. So we factor out h. We've got h over h times 12 plus h over h. Those cancel. Now, as h goes to 0, your limit is 12. We have the same thing in number 14, which is our last question. So the function is negative 2x minus 7, and then x is 9. So f of x is that. So we have negative 2 times 9 plus h minus 7 minus, and we plug in the 9 in there, and we get negative 2 times 9 minus 7. So negative 18, distributing, minus 2h minus 7 minus, inside here I have negative 18 minus 7. So here I've got negative 18 and a minus 7, that's negative 25, minus 2h. This is a negative 25, this is a minus, that becomes a positive 25. So now the 25s are gone. I have negative 2h over h. Limit as x approaches 0, cancel out the h's, and you are left with negative 2. All right, that should get you through the problems for 2.2.